All right, here's our bell work. Determine whether the table represents a linear or nonlinear function, and then we'll go ahead and explain. So looking at this first table here on the left, I'd say, well, 50, this goes down to 35, which means it's some kind of decrease. So I got to show this with a negative. And to figure out that distance, you just subtract the two. 50 minus 35 is 15. So on the graph, this would go down 15. And then the x's, this tells us how far to the right this would go from 2 to 4. That's to the right 2. So this gives us a ratio or rate of change of negative 15 to 2. And then we'd check the next set to see if they are the same. If they're the same, then it's linear. If not, then we don't worry about the rest of them. If it is the same ratio, then we continue through the table. So 35 down to 20 would be down another 15. And 4 to 6 in the x's, that's to the right 2. So that's another 15 to 2, negative 15 to 2 ratio, which is the same. And then 20 down to 5 is down another 15. 6 to 8 is to the right 2 as well. So this shows that it has a constant rate of change or ratio of change, which makes this linear. And then for the table on the right, starting with our rise, which is in the y's, this is going from 1 to 16, that's up 15. 16 minus 1 is 15, and then up from 1 to 4 would be to the right 3. So that's a 15, positive 15 to 3 ratio. And then from 16 to 49, that would be up 33. And I just did 49 minus 16. And then from 4 to 7, that's to the right 3. So that's a 33 to 3 ratio. And yeah, you could have seen perhaps that 15 over 3 simplifies into 5, and 33 over 3 is 11. In either case, though, you'll see that the ratios are not the same. If you're just looking at the fractions, the denominators being the same tells us we have a different amount in the numerator. So these couldn't be the same, even if you just looked at the fractions. A good question is, if by chance, maybe your x's went up by 4, but it depends on your rise, right? Because we're looking at this as a ratio. So let's say that it went down 30. Well, this ratio has the same value as this ratio. So if we had seen something like this, then it would be linear. So we're actually equating this. And yeah, you could say, well, I'm just going to look at the decimals as well. Like this one would be negative 7.5. This one also would be negative 7.5. It's the same exact value, which makes the ratio exactly the same. Objective, 2 objectives. The first one, I can sketch and interpret graphs from any situation. And then the second one, I can determine when graphs are manipulative. Just take a minute and copy that down, please. First couple here, we're going to be sketching a graph to match each of the following stories, and we'll label key features of the graph. The first thing I would recommend when looking at these problems is at least to read it. You may have to read these a few times to really get it down. So like first up, it says, Zach walks home from school each day. Sketch a graph of Zach's distance from school as a function of time. Since the bell rang, if the following happens. When the bell rings, Zach runs to his locker to grab his books and starts walking home. When he's about halfway home, he realizes that he forgot his math book, so he turns around and runs back to school. After retrieving his math book, he realizes that he is going to be late, so he sprints home. Now remember that we're looking at distance. It's not just distance, it's distance from the school. What that also tells us, because there's no scale on either of the axes, what that tells us is that 0 right here, that's the same as being at the school, okay? So this is at the school. Put that in. And then the time, now the first thing we see on this is it's a function of time since the bell rang, okay? And yeah, remember it's always y is a function of x. So we would know that distance is y and then time is x on this one. But what do we know about the time? Well, when the bell rings, that's the first thing we see right there. So in time, the first thing that we notice is that the bell is going to ring. So that would be the first thing that happens, or that we're going to put into the scale right there. So when the time is 0, we're going to start that as 0, which is when the bell rings. Well, then Zach is going to run to his locker and grab his books. So that shouldn't take too long. So I'm just going to put another line here, which is going to represent his locker. And so he runs to his locker to grab his books, and then he starts walking home. Now, at some point, of course, at the end of this story, we assume he'll make it home. All right, and I know that sounds more like a distance, but I'm looking at more in terms of when he'll get home, which is some form of time. So he's going to start walking home, but when he's about halfway home, after walking, he'll realize he forgot his math book, so he turns around and runs back to school. So some of that has more to do with distance, but at some point he's going to forget his math book. So he said he's about halfway home at that point, so I don't know. In our timeline, I'm going to put it right here. Actually, I want it just a little bit farther to the right. So this is when he forgets. He realizes that he forgets. And then he's going to run back to his locker, so that I'm going to put another mark here, about right there. And that will be another point at which he's at his locker. And from there, he's going to run home. So you see that from the time he was at his locker and walking home, I made this purposefully bigger than this part of the domain, because he's going to run back to his locker. So this should be shorter than this length right here, okay? And, well, then he's going to run home, and that's good, okay? So that's just based on the time. So for distance, of course, the maximum distance would be when he gets home, right? Now, there's another one we should be aware of, and that's about halfway home. So I'm going to put that mark on there. And now this should be enough information to put this graph down, okay? So we're going to say, all right, he's in school, the bell's going to ring. So I'm going to use blue, which is going to represent the actual line, okay? So he's going to go to his locker, which is that first mark, and he's going to get his stuff, put in his bag, and then he's going to start walking home. And then it did say when he's halfway home, that's when he realizes he's got to go back. So now you could put this line a little bit past that, but at some point he's going to be right here, which is halfway to his home. So he's just walking home. We'll say that's a constant rate of change on that, which means it should be straight at that point. And then that's when he noticed that he's forgotten his math book, so he runs back to his locker. So that's this mark right here. And we see that the second line is just a little bit steeper than the first one when he was walking. So in fact, I'm going to go and put that on there. This is when he was walking. And this is when he was running. All right, now at his locker, of course, it's going to take a little bit of time at his locker. So I don't know how much time. I'll just give him that much time right there. Okay. Now for me, I would say that sprinting is faster than running. So yeah, I would expect this last line to be a little bit steeper than the running line right here. But I know he's got to get all the way home, so that would be, at least the way that I have it, it should be up here. And that's where this will end. So from his locker, he's going to start sprinting home. Yeah, it's not a straight line, but it'll work. And yeah, we'll say this is the sprinting part. I'll put this on here. This is where he was at his locker. Now, the thing about these graphs is, do they have to look the same? No, they do not. Some of you would be maybe even in your mind adding more things, like maybe he's got to stop at a crosswalk somewhere in here, and so maybe there's a little bit of a flat line in that waiting for the crosswalk. I'm not going to make it that complicated, But your graphs should look pretty similar to this, but again, do they have to look exactly like it? Not necessarily. And this should bring up into your mind some questions about the validity of some graphs, because can they be manipulated? Yes, they can. And that is one of the main problems with graphs, is yeah, they can be manipulated. Two, this one has scales on the x and y axis. The x-axis, of course, is not time, it's time. And then we got number of people. I'm going to say that's number of people at the concert in this one. Let's read this one out, okay? Number two, a concert for a popular rock group is sold out. The arena holds 8,000 people. The rock group is scheduled to take the stage at 8 p.m. A band that is not very well known is opening for the rock band at 6:30 p.m. The rock band is scheduled to play for 2 hours, and the staff working the concert have been told that the arena must be cleared of people by 11:30 p.m. Sketch a graph of the number of people in the arena from 5 p.m. to midnight, with the time 0 on the grid being 5 p.m. So I'm going to put these marks down just so we know what time we're looking at. So 0, that was 5 p.m. it said. So after 1 hour, that'd be 6 p.m., then 7, then 8. That's one of our key times. And then 9, and then 10, 11, 12. 11:30 is one of our key times as well. And then, yeah, once we get to 12, we're in the AMs at that point. And what do we know about the arena? It's holding 8,000 people, and it's sold out. So I'm going to assume that it's going to be at capacity at 8,000 people right here, okay? So this is sold out at 8,000. Now, of course, at this point, there's some very subjective values that we're going to have to look at, such as the band that's coming on before, the rock group, is not, it's not quite as well known, right? So, some of those key times are, right, 8 p.m., that's when the band, the rock group, rather, will take the stage. So this is when the rock group, we'll put group, that's when they take the stage. And it did say that they're going to play for 2 hours, which means that 8 p.m. is when the group goes on, and 10 p.m. is when the group goes off stage. Okay? And another value we need is 6:30. That's when the band takes the stage, and that'd be right between 6 and 7 right there. So this is when the band comes on. And then the other time that we need to be aware of on this is 11:30, which we talked about. 11:30 is when they need to have it cleared of people, so I'm just going to put empty at that time. Okay, so we've identified the times, which is good. And in fact, we've identified the people. The empty part on the x-axis tells us that there'd be 0 people. So at 11:30 on, there shouldn't be any people left over from the concert. Okay, so you can put that straight line there. I'm going to wait though. All right, let's go ahead and start putting the graph on now that we have some of these values. So at 6:30, this is when the band goes on, not the group, but the band. Now they're less popular, and if maximum capacity for the group is 8,000 people, I'm going to put this at just a little under half of that. Half, of course, is 4,000. So my mark is going to be at 3,000. When this band comes on, a little less known, maybe you'd expect about 3,000 people coming in, okay? Now, when do they start coming in? I don't really know. I'm not really a concert person, but we'll say that maybe they started filing in at around 5:30, about an hour before. And I'm just going to make this a straight line. Well, you could make it a straight line, which would indicate that it's a constant rate of people coming in. Some of you would say, well, this one's not as well known, so maybe it looks more like this, right? They slowly come in, and then they speed up until this group takes the stage. Now, we do need to identify the rest of this part of the line to the left. Yeah, there weren't any people in there until about 5:30, and then they speed up. We speed up the number of people coming in. And then at 8 p.m., that's our next major mark, right? That's when the actual group takes the stage. So I'm going to put this point up here at 8:30. 8,000 people. And so when the band comes on, that's an hour and a half before. So again, you could put like a straight line right here. I'm not going to do that because, I don't know, it just doesn't seem logical in my mind. But you're welcome to do that if you'd like. So I'm going to say, maybe at that point, it would be more like this. Because then the number of people coming in, right, they're excited for the group to get on the stage. And that would be fine. So if you put a straight line, again, you'd say that it'd be a constant number of people coming in. But if you curved it this way, you can still justify that because there's nothing to say that you couldn't, right? Which means that, well, there's people there for the band, and then more people would come in very quickly to see the group. And then you'd expect all 8,000 of those people to be there until the group goes off stage. So that's until 10 p.m. That's this mark. So that's a flat line right there. And after that group goes off the stage, yeah, sometimes people stick around, but I don't think they do very often for too long. And we know by 11:30 it needs to be emptied. So again, you could use a straight line on this. Say, well, they're just going to empty out at a constant rate. Okay, that's fine. Some of you would say, well, you know what? They're actually going to be gone a little bit sooner than that, right? They want it empty at 11:30, so it maybe a little bit before that it'd be empty. And people file out pretty quickly, and then sometimes it can look like this. So you see how subjective that is. And yeah, from after that point, there shouldn't be anyone else left over from the concert. It's empty at that point. So we just have a straight line along the x-axis. So again, your graph may look a little different. There's a couple that should look pretty similar though, like our flat line right here and maybe a flat line somewhere up here as well. But after that, again, it's highly subjective. Your science teacher has the beakers shown. He's going to fill them with water from a faucet that runs at a constant rate. Your job is to sketch a graph of the height of the water in each of the beakers over time. So beaker 1 here, we'll just say this is kind of a normal beaker, right? And so as this starts to fill with water, we see that since its faucet is going at a constant rate, it's just going up at a constant rate as well. There's nothing about this beaker to say, well, it's going to change its trajectory when we relate the height of the water with time. And yeah, it did say he's going to fill with water. Your job is to sketch a graph. It's the height of the water over time. So this is y. Y is the height. X is time. And you can put these labels on here if you need to, but it's not really necessary that you do. So height and time. Of course, it's going to start with 0 amount of water. So the height would be 0. And then at this point, I'll try to make this look a little pretty. I'd say, hey, look, this is it's kind of a straight line, kind of, I guess. And for me, this is about what I would expect this to look like. Okay, it's just the height is going to go up at a constant rate on this. Now, I'm also not putting an arrow at the end because right at the tip of this beaker, like if he kept going, it would just start pouring over, which would indicate that the height no longer is changing. But we'll assume that he stops the water from going in once it's reached maximum height in this beaker. So that's what we would expect this graph to look like. Beaker 2, your science teacher has beaker shown. This one, again, he's going to fill it with water, but it's shaped differently, right? Now think about how the height of the water is going to change here at the bottom, which I think is pretty important, okay? Because it's wider at the bottom, but as he puts more water in this thing, it's going up faster and faster. See that? Until it gets to, I'm going to call that the neck. So the graph on this one, he's got to get to the point where it gets to the neck on this, and so I'm kind of over-exaggerating this, but I've got to show that it's getting faster and faster as he puts more water in, and I have to do that with a curved line like this. Now once he reaches this neck, it's just going to go up at a constant rate at this point. But it's steep. It's a lot steeper than that last one we just seen. So that's not exactly how it would be, but it would be a straight line steep at that point until it's full. So yeah, this graph, it's approximately what it would look like. This one, same thing, except for, see how it's getting wider? It's getting wider here at the top. Yeah, it's much wider at the top than at the bottom. So as he starts putting in water at a constant rate, it's getting slower and slower because it's getting wider and wider. Now you could say, well, it's getting slower at a constant rate, which is true because it's just a straight line along the side there. So this one's going to fill slower and slower. And so for me, again, it's going to start at 0 here. Well, it starts out faster than slower, so I'd say it's going to kind of, it's going to kind of level off. Something like this. Okay. Because in the beginning it was much faster, but towards the end there it starts going, we could say, really slow. This one is interesting because it's curved, which is fine, but we can see right at the halfway point of the curvature, it's going to change, right? So if I start putting in some water into this thing, then we can see as it goes up, it's getting slower and slower because it's getting wider and wider until we get to halfway point. Okay, so I would show that it's getting slower and slower, pretty much the same way we just did that last one. So I'd say something like this, right? Start out fast and slow, but then once it gets to that halfway point, then it's going to start to speed up after that because it's starting to thin out. So that would be, well, something like this one. Maybe not straight up, but something like that. And then once it gets to this neck again, then it's going at a constant rate, which means that it should be a straight line after that. I'm just going to put that line. But again, there were 3 parts to this. The halfway point in the circular part, and then once we get to the neck right here, that's where this point is. So that's what we would expect this graph to look like. It's very similar to the one we saw 2 beakers ago. It's just that the very tip of the bottom of this beaker here is a point. Okay, so this one, it's going to start out really fast actually as you start filling this up. And then as you get up higher, then it gets slower and slower until you reach the top. So I'm going to draw this one a little bit differently than that last one, but I need to show some curvature on this one because as it goes up higher, it's going to get slower, right? So it's going to go really fast, and then it's kind of leveling off here at the top. Maybe that's kind of exaggerated, but that's what we would expect this graph to look like, something like this. Again, if we were relating time or height at the time. Now remember, on these types of problems, you can manipulate these graphs depending on your scale, right? This one did not give us a scale, which means that perhaps you saw something like this depending on how the scale was for time or even for height on that. And yeah, that changing the scale can change the way a graph looks, which should tell you a lot about graphs that you look at through social media or any type of media, really. Is the scale really what it should be, or have they manipulated it to look a certain way? All right, this graph, we got number 4. Ben and his family took a road trip to visit their cousins. The graph below shows their journey, and we'll label the key features of the graph. All right. So the first thing I notice on this graph here, just at the y-axis, the label, is the distance from Las Vegas. And then the x-axis here is time. So we're looking at how long it takes for them to get to Vegas, or it really more specifically, it's how far away are they from Vegas in relation to the time that we have. So right here at the top, 450, right? That's this point right here. I'd say, well, that's probably where they started. So that's probably where their home is on this one. So they're going to start at 450 miles. and again, this is away from Las Vegas. And then what? Well, what do you get at this point is a straight line right here like this. So that straight line indicates that they're traveling at a constant, in this case, speed, right? Because they're getting closer and closer. So this is showing a constant speed. Specifically, it's a constant speed, but see how the distance from Las Vegas is going downward? That also means that they're getting closer to Las Vegas as we go down, okay? And then, right here, that's, looks like that's 75 miles. Right there, 75 miles right here. Well, once they get to 75 miles, it's a flat line. So their distance now from, what is this, 5 hours to 6 hours, it's not changing. So some kind of stop occurred at this point. Maybe it stopped to get gas or something like that. Maybe it was to get some food and gas. Who knows? Who knows? But it was for a full hour that they stopped. And then this next one, this next part of the line right here, we see that it's not as steep as the purple line right here. So this means that they were not actually traveling as fast as they were before, but it's still a constant speed because it's still a straight line. So right here, it's a constant speed, but it's a little slower. That's a slower constant speed. I know that's small writing, but hopefully it works. Maybe this helps. All right. Well, at this point here at the bottom, that means they actually are in Vegas. Okay? So this orange point right here, that means they actually are in Las Vegas, or at Las Vegas, however you want to say it. Now, did they stop in Vegas? No, if they did stop in Vegas, it would have been some kind of flat line at this point, but they didn't. Looks like they went straight through Vegas at this point, so I would say that they actually continued the trip. Some students would say, well, they got to Vegas and then they came home. I don't know. Maybe there was some kind of avalanche out there in the desert. But in any case, yeah, I mean, you can find your reasons and say, well, then they turned back home. Maybe they got a flat tire. I don't know how that works, but students have said that in the past, okay? So I'm going to say that they continued this trip, and not only did they continue the trip, but it looks like they've returned to their speed that they have before. And I'm not going to calculate that exact speed because I don't really care. We're just kind of analyzing this graph. So then they speed up at this point, but they're going past Las Vegas. So this one is they speed up past Las Vegas. All right. So they go past Las Vegas. That's what I'm going to say. And it's up to this line right here, which is at 225 miles. Now, I'm not too familiar with Vegas and going past it, but I think that's around Los Angeles. I could be wrong about that. I suppose I also don't care. But in any case, right here, they stop again, right at this blue point. They stop. How do we know they stop? Because it's a flat line. Okay. So for me, I'm going to make the assumption that this is where they arrived at the Cousins. And you could say, well, maybe they just stopped somewhere on the way to the cousin's house, perhaps. But since they are going to the cousin's house, we're going to assume that this actually included the full trip. And if you wanted to, you could say, well, they went past the cousin's house here, and then they went to Vegas and then back, right? Which would show this part right here. I don't know. However you want to do it. But again, just the fact that you're able to interpret these differently indicates that, yeah, there's a lot of subjectivity to graphs in general. Yeah, you could have written all this garbage. I'm not going to, as much as you may want me to. In fact, I'm not even going to read it, but you're welcome to if you would like. So, number 5, I'm going to say Jorge on this one. Jorge is the team captain of a soccer team. He would like to order shirts for the team and is looking into how much it will cost. He called Custom Tees to ask about pricing, and the manager sent him this graph. And yeah, we should be able to see the prices of these T-shirts at these graphs. Now, when we look at these lines right here, you're going to notice 2 different type of circles on this. Right here, this one's I'm going to say that's a closed circle. Same with this one. And that should remind us of the inequalities unit, because just below it is an open circle. Remember, if it's an open circle, that means it's not included. So at least for this first stretch, I think that's up to 10 T-shirts. So if you purchase 0 to 10 shirts, no, that's supposed to be shirts. 0 to 10 shirts, it appears that the cost will be $16 per shirt. All right? And yeah, you may wonder, well, why is it costing us money for 0 shirts? It's because, they may have purchased some stuff for you if you've made the order. The shirts, the ink, or however that works with shirts, and maybe set up the machinery, which does cost money. And so if you're canceled by chance, then they would have kept that money. Now, why does it go all the way to 10, which is this first line? It's because it's closed right here. It's open here at the next line. And yeah, that line is going to be, looks like that's $14 right there. So the next set, this next line right here, I get an open circle here and I get an open circle on both ends, which means that, and of course this is beyond 10 shirts, so I'd be starting at 11 shirts, going all the way open at 30 right there means that somewhere between 11 and 29 shirts, this is going to tell us the cost. So that's, what is that, $14 per shirt? And then the next line, yep, we got a closed circle there and a closed one there, which means that 30 and 50 are included in this next set. And that is up to, looks like $10. So this is from 30 shirts to 50 shirts for $10 each. I did label that a little differently just to show you that you can. And then the next line, this is open at 50, which means that it would start at the 51st shirt all the way up. It's not including 100. So I'm going to say all the way up to 99 shirts. This is going to be, yeah, that's right on line with $8. So $8 per shirt. Now, could you just say 51 or more? You could. But since it's showing an open circle at 100, I'm going to say that specifically they stop at 99, which also perhaps means that maybe this company will not make more than 100 shirts at a time. Who really knows? That's just all the information that was given to us. And yeah, the other question that should come up is, I mean, why is the soccer team ordering over 100 shirts? I don't know. Because this is just for the team. If it said like for fans or something like that, you could maybe understand that, like they're going to sell the shirts. But I don't know a lot of soccer teams that need, 10 shirts per person-ish, something like that. Maybe it's like tackle soccer and they rib the shirts a lot. I don't know. Yeah, there is this. This is just what we wrote, but in words, like a paragraph. If Jorge orders 0 to 10 shirts, he will pay $16 per shirt. 11 to 29 shirts, he will pay $14 per shirt. 30 to 50 shirts, he will pay $10 per shirt. And 51 or more shirts, he will pay $8. And again, we were more specific than just 51 or more. Specifically, it was for 51 to 99. Number 6, a boat is anchored near a dock. The graph below shows the distance from the bottom of the boat to the seafloor over a period of time. We need to tell the story of the graph first. So for those of you that are like, man, I love English class because we get to write so much. This is your opportunity. And yes, I'm not gonna like make a novel out of this garbage, as much as you may want me to. I'm just gonna, well, kind of consider what the crap is going on. So remember that it's the bottom of the boat, it's the distance to the seafloor. That's what this is showing. So why is it going up and down? And hopefully this would make sense, right? Because there's somewhere in the sea, some sea somewhere, which would indicate that you got waves on the sea, right? The boat kind of rocks up and down. And, it's between 14 and 16 feet, right? It goes down to 14 all the way up to 16, 14, 16, 14, 16. And, yeah, I don't know that 2-foot waves are like enough to get seasick. Some of you guys might get seasick just looking at that garbage, but I think that's more because of the math. This story would be adequate. At time 0, the bottom of the boat is 15 feet above the sea floor. And that would be, I would say that's important to notice right there, 15 feet above the sea floor. After 1 second, the boat is 16 feet above the sea floor. Then it drops down to 14 feet above the sea floor. And then I would just say that it kind of repeats that process from 16 to 14. So the boat could be bobbing up and down in the water due to waves coming in. That seems substantial for this. All right, number 7, the graph below shows the amount of gas remaining in a vehicle over time. Tell the story of the graph. Okay, well, let's look at the graph first. Let's kind of analyze the graph. Then we'll tell this fun and exciting story. So what do we start with on this one? Yeah, they're going to start with, that's between 20 and 16. That'd be 18. And, yeah, we got the label up here in gallons. So they're going to start with 18 gallons. And we can see right here that it takes 8 hours for it to go from 18 gallons. And I don't know if that's full, by the way. It's just 18 gallons to 0. You can assume that it's full, though, if you'd like. So let's say they're going to use this gas up at a constant rate. Okay? So I'm going to go ahead and put that in there for this red line that we got. They use the gas at a constant rate. Yeah, that looks pretty good. Okay, well, they're using the gas at a constant rate. Sorry, typing's hard. But what does that mean also? That means that they're traveling somewhere. Right? They're traveling and they're using up the gas, but at a constant rate. So maybe they're able to go at a constant speed as well. And then what happens? Well, you get this, I'd say that's straight up and down, but right at about 8 hours here, the gas tank goes from empty, which was the green point, back to 18 gallons. So again, this is why I would say, well, maybe we're justified in assuming that this is full, because they started at 18 gallons, they used it all up in 8 hours, and then it goes back to 18 gallons. And did they use any gas after that? No, they did not. Right here, this is a flat line, so they weren't actually using any gas. And then, actually, it looks like the rest of the time here, and yeah, that is from 12 hours to 20 hours. That's another 8 hours, just like it was before, 0 to 8. So they're using the gas again at the same rate. So this one over here, they use the gas at a constant rate. Yeah, we're going to say the same thing over here for this red line. Until it's empty again, right here. Now, that's as far as we need to go. Yeah, blue. That's as far as we need to go because this is all the graph shows us. Did they fill the gas tank up again? No. Maybe it was their getaway car and then they dropped it off somewhere and then they walked the rest away, or, some kind of accomplice picked them up. Maybe I shouldn't be using that example in school either. But in any case, that's what I'm going to say about this. So I'm going to say that this represents the graph. And yes, could you write a story about it? Sure, you could. The car starts with 18 gallons of gas in its tank. The owner is driving the car for 8 hours and gas is being used at a rate of, we didn't figure out the rate and that's fine, it's 2.25 gallons per hour. At 8 hours, the tank is empty. The owner fills the car with gas and lets it sit for 2 hours for some reason. Maybe they stop to get a drink or a meal or take a nap. Maybe it was to stop to take a nap and eat a meal. I don't know. But then the owner starts driving the car again using the same rate of gas, 2.25 gallons per hour. After 8 hours, again, it is empty. So that brings us to the objective. I can sketch and interpret graphs from any situation. And again, this bottom part, we should be able to tell if graphs are manipulative just by looking at the scale. But also, we've kind of learned how to manipulate graphs. So like in the future, if you guys ever run for like student council, just make graphs that manipulate people's brains, and you should win. You should win, as long as the other person doesn't really know what you're doing, you know what I'm saying? Yes, they use this a lot in politics. And yeah, we just came out of a political season, so did they use these? Sure did. Yes, they did. And they'll still use them, by the way. Which is why I think that's very important for you guys to know.